All righty. Yeah, my cats woke me up at like 3:45 this morning, so I just got in the car and drove out to an open spot. Tried to look for the comet, did not find the comet at 4:30 in the morning, and then went back to bed. So if you guys see it, take a picture, share it. I think it's starting to come up now more about sometime after sunset now, sort of in the northish, northeast, northwest, somewhere in that area. It's moving towards the west. They say you can see it with your eye. I don't know. Those fancy pictures, if you've seen them, are probably with telescopes with filters and total cheating. But anyway, what do we got? Let's do another one of these examples, and then we'll move on to two other kinds of work. I definitely think we're going to stop at 7.5. We'll pick up 7.6 later. So this is example sort of, so you have the stuff in front of you can read through. We don't provide every detail. So here's the deal. This one is putting a few things together. So it's a good one. And we're now going to be going back to English units here. So for some reason, we like to stand on top of these cliffs, 50-foot cliffs, and you have a rope and you're lifting now a box here. So you have a box down here. You're lifting it with a rope, and so you have the rope, which it says the density here, and yeah, I'll just put it right. So the density is 2 pounds per foot. So now we have we're going to be dealing with foot-pounds. So you need to make sure we get our stuff set up. And then the nice thing about it is if you're dealing with pounds, you already have the gravity like figured in. You don't have to worry about multiplying it by 9.8, or in this case, 32 feet per second squared, because that's already built into the pounds. So if you're like, wait, why do I have to do 9.8? Well, that's because it's not built in for the newtons. You're going to need to multiply by 9.8, but you don't have to worry about multiplying by 32. So in some sense, that's a little bit easier. Now, on the bottom, you have a box, and the box weighs 5 pounds. So the box is 5 pounds. But, of course, just to make it harder, we have 100 pounds of sand in the box. All right, so you've got a box which is 5 pounds, you've got 100 pounds of sand, you're lifting it up with a rope which has a certain density. The question is, how much work do you do?
Can we just add the box and sand pounds together to make it easier, or no?
No, because guess what? Your box is faulty.
Oh, great.
So what ends up happening is the sand is actually not the vegetable leak, but it is leaking out at the rate so that by the time you get it up to the top, and again, you figure out the leak rate here, is it says by the time you get up to the top, you're speeding, or you got this hooked up to a machine or something. It takes you 60 seconds to get the box and everything up to the top. But by that time you get to the top, the sand is gone. So it all leaks out and we'll assume it's at a constant rate, so we don't have to worry about, like, does it leak out faster at the beginning? I don't want to have to deal with that.
We'd find a derivative of the rates of the leaking of the sand.
Yeah, I'm not doing that. We're gonna say it's leaking at a constant rate. So how much? Thank you. So how much is it leaking out by? Well, we'll deal with that in a second. So you have sand that you're not just taking the 100 pounds of sand and lifting it up, because that would be too easy, right? You would just 50 and multiply it by 100 and you'd be done. So what you're going to need to do is you're going to need to work this out in 3 pieces. Look at the work that you do on the rope, the work you do on the box, and the work that you do on the sand. And then you're just going to add them up. So you just add those up. So we'll figure out what those 3 things are, and then we'll just add them up.
Well, the sounds to me most difficult because it's leaking at a constant rate, which means there's less of it. It's being subtracted by a certain rate.
That's right. So it's 100 at the bottom, but at the top, in the middle, it's going to be 50, and then by the top, it's going to be zero. It's going to be 0. Although actually I did change the problem here, so I don't want to do that. So a box of 100 pounds, we'll make it easier. It's 100 pounds of sand. It's leaking at a rate. So I mean, you could work it out so that, I don't know, 100 over 60 doesn't work out so nice. So let's assume it's leaking at every second it loses 1 pound. So it doesn't end up at the top empty, but it still takes you 1 minute to pull everything up. Yeah, so if you wanted to make it empty, then you just change this rate to be 100 over 60. So if you wanted it to be empty. But this problem actually just says 1 pound per second. So at the bottom, it's at 100. At the top, it's going to be 40 pounds because it loses 1 pound for every 60 seconds. All right, now the box is the easy one because the box is always 5 pounds. So it's like it's like the rock. So the work done on the box really is just the force times the distance because you have to move the whole 5 pounds all the way. So that one is just straight up 5 pounds times 50 feet. That's a straight up, no calculus required, 250 foot-pounds to move the box. To move the sand, well, the problem is it's going to be an integral.
Hang on, where 5 from? I thought the box weight was 15 pounds, not 5. Oh, never mind. I see. I'm reading the is of 15. Sorry.
The is, right, yeah.
Yes.
Yeah. The letters in the English alphabet that are terrible, right? What is that? What is that symbol there? It is either a 1 or a lowercase l or a capital I, depending on the context. How about that? That's either a 0 or an O. We don't know. Actually, if you look in your car and you look at vehicle identification numbers, they deal with this by saying, if you see this, it's a 0. There's no O's in a vehicle identification number because they're like, that's just dumb. I think we should have evolved to a point where we can have different symbols to mean different things. Okay, that's another tangent for today. The work done on the sand will be a force times a distance. The problem is that over time, the 100 decreases. It decreases. So how much is it decreasing? Like every second, how much is it decreasing? So well, let's see. So it's at one pound per second. So that means that at the bottom, we've got 100 pounds. At the top, it's got 40, right? Because it lost 60 pounds along the way. But the problem is I'm going to want to chop this up, not in seconds. I want to chop it up in feet. So if it's 1 pound per second, how many pounds is it losing per feet? So it's losing 60 pounds because I said it was 1 pound per second, so, and it's 60 seconds. So it's losing 60 pounds, but it's only moving 50 feet. So how many pounds is it losing per feet? And the answer is it's 1.2 pounds per foot. So you can, and really all that is that's 60 divided by 50. So it's 60 pounds in 50 feet. And so that's where you get your pound per feet. So it starts off at 100. 1 foot later, it's at 98.8. And then it goes to 96.6 and then 94. It's like going down by 1.2 each time. So the formula for this, as we just did on the previous page, it is a Riemann sum, but in the end, it ends up being an integral of 0 to 50, because I'm going up, x is going through 50, and then what I'm integrating will not be 100, it will be 100, but I'm subtracting off 1.2 for every foot that I go. So 100 minus 1.2x. And so that's the idea. It's like how much sand is left as you're moving it through. So you take away 1.2 pounds for every foot. And again, x is like feet. So you get that. Similarly, for the work for the rope, coming back up to the top, I'm still moving at 50 feet. But what's the weight? Well, the weight will be however much rope is left. So that's 50 minus x. That's the rope that's left, just like we did on the previous problem, multiplied by the density. So 0.02. That will give me my force. When I integrate that up, I will get the overall work. So the idea is think about how much is left and integrate that over the range that you have. In this case, this is measured in pounds. This is measured in, well, you got to multiply feet times pounds per feet. And that's what this is. So it's like feet times pounds per feet. And that'll also give you pounds. So those three forces, you work them out. So work out and add. And they're all just x integrals. So I think that's not too bad.
I'm still confused as heck for the work for the rope. Exactly. How'd you get 50 minus x? I'm still lost on that.
Well, the idea is, if you think of this as a Riemann sum,
Mm-hmm.
you have to move the entire rope 1 foot. That's for sure.
Yes. After
you've moved it 1 foot, you have 49 left.
Oh, okay. And so you're subtracting 1 for each time. Okay, I get it.
That's right. The problem is I don't tell you that x is equal to 1. X is how much you move it the very first time. So it could be you move it an inch. You have 50 feet minus that inch left to move. And so it's 50 minus however much you move it. The integral means you add it up over all possible movements. If it's 1 foot at a time, it'd be 50 things added up. If it's 1 inch at a time, it would be 50 times 12. It would be 600 things that you have to add up.
Okay.
But at each time, you're just subtracting off how much you've done to that point.
Okay. Yeah. And for the for 1.2, I understand the math you did, but I thought that because it was pounds over seconds or pounds per second, it would be 50 over 60. I was kind of wondering if that was the case. It would actually be somewhere around like.
So if you leak at 1 pound per second and you wait for 60 seconds, then you've lost 60 pounds, right?
Okay, yeah, never mind. That doesn't make sense. I understand.
It's just a fraction. You got to make sure that the pounds are on the top and the feet are on the bottom. So it is 50 pounds per 50 feet. So
okay.
That's how that works.
Okay, I just want to make sure.
So yeah, no, I understand. I mean, that's the hardest part right there. It's basically trying to figure out what goes there. The rest is easy. It's the density for both cases, and then whether it's a metric, you have to put in a 9.8 in order to get to newtons. If it's already in English units, everything has already got pounds, so you don't have to multiply by 32 or whatever the gravity is in those units. So yeah, so we got that. The remaining part here, how does it get harder? I mean, it really is just, here you've got the rope, it's like nice and uniform, and so you'll have these fairly nice formulas when you're working it out. Same thing turns out to be, we're in physics day here, so you probably remember something that's called Hooke's law, and this is for springs. And so it turns out that the force equation for Hooke's law is just a constant, times basically how far you stretch it away from its sort of the spring's natural length. So this is the spring constant for the spring, and it'll be, it depends on what the spring is made out of. If it's really stretchy, You know, you'll have a different spring constant than if it's like the shocks in your car. So it's sort of how much force you have to impart. If the springs in your car, you have to put a lot of force to move it. So the spring constant is going to be high. X is going to be how much the spring is moved. So this is like the distance the spring is moved from its natural state. So if you have a spring that's just sitting there, good. You know, that's its natural state. If you took it and you either compressed it or you stretched it off of that, then X represents how far you've stretched it off of that. And if you haven't noticed up to this point, here's the nice thing is the really condensed formula for all of this is that the work is just the integral of the force. So that really is the condensed, and that's exactly what we've been doing up to this point. Finding the force of gravity on a rope or on sand or on a rock or on a box. So in Hooke's law, all I really need to do is I just need to find out what this force equation is and then integrate it, and I'm done. So these are actually fairly short. So we'll just keep, I think, going through these examples because there's, you know, fuller details in the book. But it says that if you apply a force of 20 feet, 20 pounds. Yeah, so we won't use, we'll go back and forth through the English system here. A force of 20 pounds stretches a spring from 7 inches to 12 inches. So the 7 inches there is the natural state. You have a 7-inch spring, and you apply a force of 20 pounds to it, it stretches it out to 12 inches. Then the question is how much work did you have to do in order to do that? So, well, the work, for this is the integral of the force equation, and the force is just the spring constant times x. So that's for Hooke's law. For the work, we just have this integral. So we need to figure out what k is, and we need to figure out what the bounds are. So for the spring constant, well, it says you applied a force of 20 pounds, and it stretched it 5 inches off of the natural state. So you might remember this definitely from physics, is that it said that when the force is 20 pounds, the distance I moved it was 5 inches. And now is enough to just figure out what the spring constant is. Almost. We need this to be in units that we're used to, and inches is not that. So we're talking about foot pounds, foot pounds. So not inches pounds. So we need to first of all convert that inches into feet, and that's pretty easy. It's just 5/12 of a foot. So if you put those two things together, the spring is governed by the fact that 20, which is the force, is equal to whatever the spring constant is times the distance that you stretched it, which is 5/12 feet. So we can figure out for this particular spring, what is the spring constant. And so just multiply by 12, divide by 5, we end up getting 48. So, and I guess if you wanted units, that's like going to be pounds per foot on that. So that's going to be 48, so we can put that in, 48x. So that's my k. And then how about the bounds? Well, I mean, x is like how far you moved it. So you moved it from the natural state, so from the natural state, out to 5 inches out. And again, I'm going to want to use 5/12 because it's feet. So X is help, that's the X direction, and that's exactly the X that comes from the force equation for Hooke's law. And it's not Hooke's, it's not Hooke's law with the, like Captain Hooke's law. It's got an E in it. Sorry about that. So my integral now is I want to add up like all of these work smoothly. Again, it's going to be like the limit of a Riemann sum. And so I end up getting this equation here. So it's the integral of the kx that you get from the force equation for Hooke's law over the amount that you've stretched it. And so, I mean, you can do that. You can do that real quick, actually. So that's just 24x squared between 0 and 5/12. Plug in 5/12, and we get 25 over 6 foot-pounds. So a little more than 4. A little more than 4 foot-pounds. So that's Hooke's law. And then maybe the last one here, and I think we can revisit this as well, in case it's confusing, is this is about pumping fluids out of a tank. It looks a lot like the rope problem, except now the rope is not going to be skinny and uniform all the way down. It's going to be maybe in a conical tank. So, but it uses exactly the same principles. It's going to be like how far are you moving it, how much is sort of, you can sort of think about it as how much is left. So let's just do this one here. So this is 7.5.6. So you have a conical tank of water, as of course we all do. So you have a conical tank, and it's sitting, I think we put this at like ground level here, put the y-axis down the middle. Like a really bad swimming pool. So it's 2 units across at the top, and it's 10 units deep. And this is measured in feet. So 10 feet deep, 10-foot radius, and it's full of water. Full of water. So, and what you do is you want to hook up a little pump, and you want to pump the whole thing out. So we are going to need to know what the density of water is. And this is something that maybe, you should know anyway, is that density of water, if you measure that in cubic feet. So if you have a cubic foot of water, then how many pounds are there in that? So take just a tank that's a foot by a foot by a foot, fill it up with water. Could you pick it up? How strong do you have to be to pick it up? Could a little kid pick that up or not? So this is significantly more than like a gallon of water. It turns out that the density of water is approximately, for every cubic foot, it's 62 pounds, 62.4 pounds for every cubic foot of water. So you're going to want to take that and then pump it out of the tank with the idea of, guess what? Pumping the stuff at the top, you're not going to have to move it very much distance, but it's more water because it's wider at the top. At the bottom, it's wider, or it's not as wide, but you're going to have to pump it a lot farther. So the idea on this really is to calibrate it so that the y-axis is up and down, the x-axis is here. So you can think about this as being like 10 units below the water. So everything is going to have to travel from -10 up to 0. You can move the axis to the bottom and rejigger it. Your formulas will just be slightly different. You'll get the same answer, and maybe we can do that later. But the idea is we need to move each little strip here is not going to be like a strip anymore. So if we had our little Riemann, this is going to be more like a disc here. So I need to move that disc up a certain amount. So So how do we do that? Well, every little disk here, you're going to have to move that volume to the top of the tank. And then not only are we going to have to do that, we're going to have to move it. We're going to have to move every single one. So we chop this into a bunch of little cylinders, and you know, we're going to have to move that a certain distance up. So what is the distance that we have to move it? That's kind of the easy one in this one, is that the distance that we have to move it is actually just whatever the y coordinate is. So, or sorry, not y, but it's going to be the negative of y. And this is a little bit annoying. If you put the thing at the bottom, then some of the equations look nice and some of the other equations start to look ugly. But the distance that we're going to move it to ground level, if you're 6 feet below, that means the y coordinate is -6. So how far are you going to have to move it? You're going to have to move it 6. So whatever the y coordinate is, you have to negate it in order to get the distance. If you don't, then your answer will just be the negative of whatever the real answer is, and that's okay. You can just take the absolute value and you'll get the right answer. So the work will be the integral that you might expect. The y values are going to go from -10 to 0. And then we're going to want to know about basically the cross-sectional volume times the distance that I have to move it. And now everything is in terms of y. So I need to know what the cross-sectional volume is and multiply that by the distance. And then I also have to multiply that by the density. You might have seen that symbol before, but it's like the Greek letter delta. Sometimes they use that. So here we go. So the distance that I have to move it, if I set up my axis system this way, is just the negative of whatever the y coordinate is. You can see if I'm at the very bottom of the tank, y is -10. How far do I have to move it? 10 units. So that means I have to take the negative of whatever my y is. How about the cross-section of this? How about the volume of this sort of thing? Well, the volume of that little thing, you have to use some sort of, it looks like a cylinder. So that cylinder, if I was to chop it up, here's my cross-section of that disc. So it's technically 3D, and I'm looking at it from the side. It's going to look like a little cylinder. So I know that my volume of that little piece is going to have to be pi r squared h, where h is the height. Now, the height of this thing, because I've chopped it with a Riemann sum, is delta y. So this delta y, when I take the limit, is going to turn into dy in my formula. So it's kind of already built in my formula here. This would be like dy. The hard part is what is the radius? What is the radius of this guy in the middle? At the top, the radius is 2. So the top it's 2. What's the radius at the bottom? The radius is equal to 0. So that means that if y was 0, the radius would be 2, or vice versa. If y is -10, then the radius is going to be 0. That's at the bottom. Any point in the middle is going to have to follow like a similar triangle kind of thing. So if I knew the y coordinate, then I could get the radius. And so the nice thing you can see is that this turns out to be, what does this turn out to be? To just do a line that goes through this point and this one. So what is the, and I have to do it in terms of x now, because it's like sort of like sideways. So the radius will be what? It'll be 1 like the slope of this guy goes up 10 and over 2. So y is over run. Am I turning this sideways here? If I did it with y, no, so the y equals negative 10 plus 5x, if I wrote it out that way, or even r, because I'm sort of like r is side to side. But this is not the equation that I want because I want everything to be in terms of y. So I need to change this to bring the 10 over y plus 10 over 5. And that will be in my radius function. So I'll have technically 1/5 y plus 2. So that will be 1/5 y plus 2 would be my radius. So that means that my equation for the volume will be pi times 1/5 y plus 2 squared, and the dy I've already put over here, so this is like the radius and the height. Then I have to multiply by the density, which is 63.4, and then I multiply by the distance that I have to travel. It's really like sort of cross-sectional area to get the volume, multiply by the density, and then multiply by the distance that I have to do it in order to get force times distance, give me work, and then I do the integral to put that all together. This is not easy. This definitely takes a lot of practice, but the pieces are all there. It should be, this work equals force times distance should be in your head. So where's the distance? The distance is there. Where's the force? Well, the force is this part and this part put together as the volume times the density. So it all comes down to this. The integral is how far do you have to travel for the distance here, the total distance, from -10 up to 0. And that gives you your equation. We're going to do this again, I think on next time to test. Next time after that, where we put the axis system at the bottom. Maybe your brain will have incorporated some of this. And again, the end of the chapter is always harder than the beginning.
So where did the 5x come from?
It's the slope of the line. So it's, you go up 10 and over 2. So the rise is 10 and the run is 2. Yeah. And the y-intercept is -10. So I've got y equals mx plus b. I guess I wrote it in the reverse order, but y equals mx plus b. So you get that. But again, I don't really want the y, I want the radius of this thing because the cross sections look like little cylinders. So I figure out the volume of a cylinder, which is pi r squared h. And that's why I did then solve for x. And you realize this r here really is, it's x. It's how far over you're going. So if you convert that down here to the radius of the thing, r and x are basically the same. There's a lot going on in that one, for sure. We went from just pick up a rock, multiply force times distance, I'm done, to now I got to do an integral, and I've got my distance, and then how do I get my force? I got to do cross-sectional volumes that I then multiply by the density. Yeah,
yeah. I'm going to need OML to understand this. I need to go over a few more times.
No, I understand. I understand. I mean, the idea should make sense. Is if you want to get pounds, how do you get pounds? Well, you got to multiply pounds per cubic foot. Well, what is pounds? Pounds from pounds per cubic feet, I got to multiply by cubic feet in order for that to cancel out. Well, what are these two things? That's volume. What's pounds per cubic feet? That's density. So if I want to get pounds, which is my force, I have to get volume and density and multiply those together. I didn't have to do that in the rope because that really was more like a linear thing where I could talk about pounds per foot and feet. I didn't have, I cheated a little bit. The rope technically has cross sections that are not like lines. They're little cylinders, but if the rope is so skinny, then I can actually approximate it by just using its length as opposed to little cylinder volumes. So a little bit of a sneak there.
I was going to say, because it just seems, I mean, this wouldn't be my first reaction to the problem. That's the thing. I would have definitely taken some more wrong and different steps when I first saw it. So that's why.
Okay. Yeah. I mean,
like my first thought was turn to an integral, but my next thought wasn't, okay, I'm going to flatten the surface or get the cut the cone in half or try to find the midpoint of the cone and go from there or midline.
oh, okay. So let's see. So yeah, if you didn't know any calculus and I said, supposedly the idea is what you want to do is just lift this whole thing up to ground level. So
Yeah.
what you do is you have to chop it into a rock here, 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 and you have to lift all those things up. And you'll get work 1, work 2, work 3, da da da, and you can do that.
Yeah, that's what my first idea was. That's what I was thinking of doing.
And that is exactly fine. So
okay,
this will come from what? It will be force 1 times distance 1. Like how much force do you have? How much does the rock weigh times how much you have to move it? So it's just weight times feet, foot-pounds. But the problem is what is the weight of the rocks? And the answer is, well, in order to figure that out, I need to know the volume of the rock and multiply by the density of the rock, because this is in cubic feet. This is in pounds per cubic feet. So when they cancel, yeah, I do get to pounds. Then I just multiply by the distance. And that's exactly what I did. But trying to figure out all those volumes is not easy because they're growing. The rocks are bigger near the top than they are near the bottom. So,
okay.
So how do you figure that out? You know,
Yeah, because it just seems like that would have just made more sense to me instantly, because the section we used last, it's in 7.2 and 7.3, so I was thinking, oh, you could just do that, but that was not it at all.
But yeah, it is. It's just hidden. It's because this one I didn't tell you what the functions were.
Okay.
I just said, guess what? This is too wide and it's 10 tall. Oh, well, what are the functions? Well, you have to figure that out.
Yeah,
Okay.
That's the part.
Where do I put the axis? Well, if I put the axis at the top, then this line ends up being y equals 5x minus 10. And I got to work off of that to figure out what the radius of this is, because the volume of all of these individual things are cylinders. So I'm going to need the radius. And not only need that, I'm going to need the height. And that's actually where delta y comes in. But it'll change if I said, well, I know I need to pump it into ground level, but suppose I pretend like instead of ground level, I put the bottom at ground level and I have to move everything 10 units up. Well, if I put the axis system there, then what's the equation of that line? I don't have to worry about the y-intercept anymore because I'm going through the origin. So I'll get y equals just 5x for that line. That's nice. That'll help me with the radius. Yeah, but how far do you have to move it? Ah, crap. Now the distance is not negative y anymore. The distance will be 10 minus wherever the y coordinate is. So the height function will change as well as the radius function will change. And in this case, you can do it both ways. You'll get the same answer depending on where which one has a plus 10 or a minus 10 in the y, whether you put it at the ground level or down at the bottom. But anyway, I think we're getting close to pretty much, well, we're not quite out of time. So we have about 18 minutes or something. Instead of taking a break, let's just see if you guys have homework questions or questions about the test tomorrow. Clearly, it's not on this stuff. It stopped. Where did it stop again?
7.5?
No, that's where we're at.
Yeah, it's what you asked.
No, the test.
Oh, I'm 7.4.
Yeah, the test stops at arc length and surface area. So it goes 6.6 through 7.4. So that's hyperbolic functions, L'Hopital's rule, and proper integrals, and then area and volume by two methods, and then arc length and surface area. So there's a lot of formulas in there. So questions on any of those things?
Sir, I haven't seen like the lessons like 7 like after 7.2 to 7.4 on Canvas. I wasn't able like to see them. Like if I wanted to look at them, like to do the homework without asking you questions, like I wasn't able to see them on Canvas. Like they were not posted.
Yeah, I did do some cleanup this morning because there was a big backlog of these things. I think they may be there now. So 6.6, 6, 7, 8 are kind of here. They don't always blend together. They're not like chops, right? Because we come back, we do some homework problems. So it starts off, then we do area between curves, and then we come back and do this volume. I think this one might be misnamed. I think this might have, oh, let me check that. I'll try and rename stuff. I think this is volume by disc, washer, and shell. But then that blends over into 7.4. So I think they're all there. I'm going to do a quick check when I'm done to make sure, but I think they are. And then on YouTube, I think everything is there, but I'll double check. I just changed that like before 5:30.
So can you show me number 16, 7.3?
Yeah.
Also, this isn't entirely related, but I actually wanted to ask you talk to my homework while you're still here, because I think there might be some kind of computer error or something, because I've submitted some of these assignments multiple times on the day they were due, and then also before and also after them to be clarified because you asked me to do so.
Yeah.
And this
I don't take off for things being late in the summer here. So if they're in, I'll just take the last one and grade it. The thing is it's tricky on online, but help receive still matters.
Okay.
And so some professors are really sticklers about this. I'm not so much, but they're like, you didn't put help received on it, you get a 0.
Oh, okay.
But wait, I did all the work. So what? We're at BMI. You have to write help received, and you have to put the nature of the help received, and you have to sign it. I usually say give it back and then make you fix it. At least the first 3 times. After that, come on, guys. I mean, not you, but
Okay.
After a while, I'm like, this is the 6th time, and I've had this in my other class. I have seniors who turn in homework without help received. They've been writing the words help received for the last 1,000 days of their life, and they forget to do it as a senior. I have little patience for that one. So anyway, okay. There's way too much chatter off the side. I know I've seen the memes where it's like the teacher's talking about stuff that's not in class. This is great. But I don't want to rob you of your educational dollar. So we need to draw this, and you don't know what the bounds are because you have to draw it, figure it out. So y equals 2x minus 1. That's a line. It starts down here at -1. It goes over is slope 2. So that line, here's y equals 2x minus 1. The other one is a parabola, and it opens up, and we plot some points. And I think I've even drawn my picture poorly here. So if x is 0, I'm at 2. If x is 1, I'm at 1. Okay, that's good. If x is 2, I'll get 2, which is back to there. If x is 3, then I'll get 9 minus 6 plus 2, which is 5. And actually, when I stick in 3 on the second one, I also get 5. So maybe I should have just, let me get rid of all this because I did a bad job of drawing my picture. It actually, maybe I should have done that first. If you said x squared minus 2x plus 2 equal to 2x minus y, you figure out that the intersection points are at x equals 1 and x equals 3. Okay, that would have been better. So I'm at 1, 1, and at 3, 5, then I get this. If the line is on the top and the parabola is down below. So we're talking about that region there. At least that's the region. So now I know that if I'm going to be working with y, I know that y goes from 1 to 5. and x is going to go from 1 to 3. So that may matter, that will matter, depending on which technique that I use. So it has multiple parts. Part A, if I do the y-axis, revolution, that's my revolution. Then revolving it, I've got my little thing here. I don't know which one you want to use. I think you probably do not want to go side to side because you're going to have to solve for x. So if you had to solve for x here, it's not terrible, but you're going to have some square roots and stuff. So I think it'd be nice to avoid that, which means I don't want to go side to side. I want to go up and down. So I want my strips to be up and down, which means it's parallel to the axis. So I am going to use the shell method on that. We've already discovered, so the volume would be 2 pi. If you're going around the y-axis, then the radius is always just x. So that's pretty nice. The height of this guy is going to be governed by how far is it from the bottom curve up to the top curve. So if I bring my piece back here, I've got the top curve, I've got the bottom curve, and then if I subtract them, I'll get the height. So that means I need to take the top curve, which is 2x minus 1, and I need to subtract the bottom curve, which is x squared minus 2x plus 2. And that's it. And now I integrate from 1 to 3. So that's the setup for part A. So radius is always going to be x if you go around the y-axis, and we'll go up and down. That'll be x. The height will be the difference between the functions. If you subtract it in the wrong order, you're at least lucky that you get the negative, and you're like, that's wrong because it's a volume. Just switch the sign. So there you go. You can multiply all that out, integrate it, and plug in the values. The difference between part A and part B is now part B says revolve it not around the y-axis, but revolve it. Here's the y-axis. Here's x equals 1. I want to revolve it around that axis now. So you can see that when you revolve it, it's going to be around this piece as opposed to way around this. So it's going to be a smaller 3D object when you revolve it. The nice thing is the height doesn't change. The only thing that does change is the radius. So the volume will now be 2 pi, still from 1 to 3. The height is still 2x minus 1 minus x squared minus 2x plus 2. But the radius will change. The radius is now 1 unit smaller. You know, I've moved it in by 1 unit. So that means that my radius is no longer x. I have to take away a unit. That's what I said before, right? It's x minus whatever that is. If I was on the other side, which I'll do here in a second, I'm gaining because I'm subtracting a negative. Here I'm subtracting a positive, so that radius is shrunk down, which makes sense because I get a smaller object. Part C says instead, revolve it around -1. So I've gone even further out from the radius. I don't know if I can fit it all in here, but I'll try. What changes is, well, maybe I'll use some ditto marks here. 2 pi, 1 to 3. This part right here is still the same h, so that stays the same. What changes is the radius. Well, the radius now is not x anymore. I have 1 more unit that I've added on, so that's x plus 1. And really, if you want to think about it formulaically, it's x minus the minus 1. The h stuff stays the same. So all the way throughout, the h has stayed the same because it looks up and down. It doesn't care what the side-to-side motion is. That's governed by R. I'll let you work all those out.
So now if we say revolve it around the x-axis, all I have to do is put it like in y terms.
Well, okay, so let's do that exact same problem with, it's a straight line. If I revolve around the x-axis, which is not part of this problem, but suppose you did, then I think you still want the strip up and down, because I don't want to solve out. If you wanted to go side to side, then you have to get all of your equations in terms of x. And that equation, you know, it ends up looking like this. It ends up being, so let's see, it'll be y minus 1, the square root of y minus 1 plus 1. I think if you solve for x, you get that. And I don't want to integrate that, so I'm not gonna. But if you then said the strip was up and down, now you're perpendicular to your axis. So if you're perpendicular to the axis, then you have to use the washer method instead. So that means the volume of this one will now be pi. It's still 1 to 3 in dx because my strip is up and down. So I'm talking about x moving. The inside radius, the little one, will be however far it is until I hit the parabola. The big radius is going to be how far I get until I hit the line. So the big radius squared minus the little radius squared is going to be out to the line, which is, what was it, 2x minus 1, and then out to the parabola, x squared minus 2x plus 2. So that's the setup if you did that.
How did you know that the big R, the big radius was 2x minus 1?
Well, you have to know what the big R and the little r mean. That if you took this strip and revolved it around, you would end up getting, a washer. I don't know if you can see that or not, but yeah, it's a washer, and the big radius is there, and the little radius is right there. How do you get that big radius? Big radius back in the picture is however far it is from here up to where you hit the outside of your object. How far is that? Well, it's the y coordinate. You know, that distance is y. But I want everything in terms of x. So I need to know what this y is in terms of x, and that's exactly the line. So it's just it's a geometrical thing. You gotta see, is the big radius correspond to the line when I revolve it, or does it correspond to the parabola when I revolve it? So that's just sort of that conceptual understanding.
Could you go through number 11 on the 7.4 homework?
Okay. So the function is ugly, but usually it's ugly because then the derivative works out to be nice enough. So we get the natural log of x, really? The natural log of x squared, awesome. Okay, so then the range for x is from pi over 6 to pi over 2. I'm not gonna work that out, or I'm not gonna draw it. I don't know what it looks like. But the length of this is always the integral between your bounds of the square root of 1 plus the derivative squared. So what goes in there is y prime. So you need to find y prime. So the derivative of the natural log is 1 over sine. And then you got to multiply by the chain rule. So chain rule problem, I get cosine. So I get cosine x over sine x. And that goes in here, cosine x over sine x. So if you got that far, you got the setup. Did you get that?
Yeah, I got that.
Okay.
And then I changed it to cotangent squared, and then I did so yeah, I change it to cotangent squared, and then 1 plus cotangent squared is cosecant squared, and then the square root of cosecant squared. And so when I integrated, I got that from the table. But then when I tried plugging in the bounds, I got, for the first term, I got ln of cosecant of pi over 2 plus cotan of pi over 2, and cotan of pi over 2 is non-existent. So I didn't know like where it went wrong.
Yeah, let's see. Well, right, so this is, wait, so hang on. This is, so 1 plus cotangent squared is cosecant squared?
Yes.
Okay, so then I take the square root, so I get the integral of cosecant, which according to the table is the natural log. Is it the natural log of cotangent plus cosecant? Or is there a minus?
Yes.
Yeah, so this is definitely diving deeper into the table than we usually do. I'm just going to write down which number that is. No, it does have a minus on it. It's okay. So according to the table number 14 in the integrals, you get this. Now, when you plug in 0 and pi, or not 0, pi over 6 and pi over 2, cotangent is cosine over sine, right? And cosecant is 1 over sine. So we'll plug in pi over 2. This will be 0 over 1, and this will be 1 over 1. So you should get the natural log of 1.
Okay, that's yeah, that's where I went wrong. Thank you.
And then minus the log of whatever you get when you plug in pi over 6. Substituting that. Plus, and this part will be 0 anyway, and you'll have minus and minus. So it'll be the natural log of the cotangent of pi over 6 plus the cosecant of pi over 6. And you're probably going to have some square root 3's in there.
Okay, that makes sense. Thank you, sir.
All right. All right, maybe one more. We're right at time, but I'm happy to do one more. And then tomorrow morning, if we can go over the first part, questions you might have. But do you have another one right now? Anyone got one right now?
So number 14, 7.3.
Okay. It should be I think fairly similar, except now we're doing some vertically and some horizontally. Okay, so I think we did this one, but it's all right. So you have these two curves. You want to take this thing and you want to revolve it around, say, x. It says x equals 2 to start. So that means you have your region, you've got your axes, but now you want to revolve it around x equals 2. Again, you have a choice whether you want to cut it up and down or side to side. I think most times you've been doing everything with x so long that switching it up to get y's your brain takes a while to get used to that. But suppose we do. If we cut it up and down so that we can get dx, then that is parallel to my axis, so it's going to be a shell method. I know that the volume is therefore going to be 2 pi. Then I have the integral. All these bounds are going to be minus 2 to 2. So minus 2 to 2. The radius is one thing. The height is going to be given by the function. The radius is almost always x, except now you've moved the radius. You've moved the revolution axis to the right. So that's going to be 2 minus x is your radius. Again, it's either x or x minus something if it's on one side, or that's something minus x if it's on the right side. The height is just 4 minus x squared. It's just the y coordinate of that strip. So that's really the setup for part A. For part B, it's real similar. If x is minus 2, and you're moving the revolution axis on the other side, and so then the volume for the shell method will be 2 pi negative 2 to 2. And this will be x minus a minus, so x plus 2, and then 4 minus x, like that. Now, maybe not too surprising, these two end up being, I think, the same answer. They will be the same answer. Because if you revolve it around either x equals 2 or x minus 2, you still get the same shape. So if you work it out, you should get the same answer for those two. C says, now I want to revolve it around the x-axis. So that one now looks like this. So revolve it around this one. If you want, you can cut the strip sideways and do a shell, but if you prefer the strip to be up and down, probably even easier, because now the big radius is however far you go out to the curve, but the little radius is 0. There's no hole in the object. So that means it's truly just a disk method where the volume will be pi, the integral from negative 2 to 2 of the big radius, which is 4 minus x squared squared. There is no little radius to subtract off because it's 0. For part D, it now says, let's move it to where?
Y
Y
equals
equals 4. Yeah, so this is where it gets a little bit trickier. Maybe I'll draw it even bigger just for emphasis. That you want to revolve it around y equals 4. Now, if you draw in your representative strip here, and you look at the position of where little r and big R is, little r is, it's always the distance from your axis to when you first hit the object. The big R is from the distance from the axis to the outside of the object. So your little r, so it's going to be washer on this one. Washer, not this. So the volume will be pi integral. You're still going minus 2 to 2. You just got to figure out what the big R and the little r pieces are to subtract. So big R, you can see that no matter where the strip is, the bottom of it is always on this bottom line, which is exactly 4 units away. So the big R is always 4. It might need a little more room for that. The little r is the distance here. Now this distance is like the y coordinate, which is 4 minus x squared. So if you go 4 up, subtract off that piece, you'll get the little r. So it's just a simple like 4 minus x squared. If I hit over an additional r, you get up to 4. So if you subtract 4 minus the 4 minus x squared, that will give you that little r distance there. So you have tons of these, like, you've got an interval and it's broken into a hole and you have a piece in the middle. And sometimes, one of these is big R, the other is little r. Sometimes it's a number that you're subtracting. So most of these things are just going to look like functions plus or minus numbers every single time. Up here, it was the x, and I did, I had this 2 here. Here, I subtracted the negative 2. Here, I didn't have to do anything because the axis was at 0. Here, I had to add, I had to deal with a 4 in these cases. So, I don't know. It takes a while, it takes some practice, figure out where you put those numbers, but the forms are very similar. All right, I got another meeting coming up in 5 minutes, so we'll take a break there. I'll try and get as much stuff, double check to make sure everything is on Canvas and YouTube properly named. And so try to get the homework for, what is that? Well, the next homework's not due until after tomorrow.
I'm just curious though. 7.4 and 7.3 are due today, correct? Or is it just 7.3? Or I'm a little confused.
Again, I think the schedule probably says 4, 3, and
Yeah, it says 4, but you said 0.3 was due today, so I'm just trying to clarify. That's all.
4. No, the schedule says today. Yeah, today is 4.
Mhm.
3, I think we delayed a little bit, so you can turn in 3. If you're still not comfortable with 4, then give that next time. What do we have left? We have 7, 4, 5, and 6, and then we have section 1, 2, and 7. So, as long as they sort of trickle in along the way, I don't care. Let's just leave it at that. Don't
Okay.
put it off. Don't put it off for sure. I think you really should try to get all the homework done for 7.4 before tomorrow because it'll be on the test. But I'm not going to do about this deadline.
Okay.
Yeah.
All right, great. I just want to clarify that. All right, thank you.
No problem.